Okay, hello and welcome to the new term. Last week we had some geometry, and so this week I'm taking it back in more a topological direction. I'm going to talk about the h-Cobordism theorem. So this is a really celebrated theorem in differential topology from the 1960s, maybe even 50s already, mid-50s or so. Smale won the Fields Medal in 1964, I think it was, but this would have been like years after publication. But it was really, really, very popular when it came out because it allowed Kervaire and Milnor, like I mentioned in the abstract, to do things like really seriously approach the problem of studying exotic spheres. So these are manifolds that are homeomorphic to the standard sphere, but not diffeomorphic. So like topologically the same, but not smoothly the same. And the h-Cobordism theorem actually gives you like a check, easy check to determine whether something is diffeomorphic to the sphere. It can be a little trickier to see that something's not diffeomorphic to the sphere. But maybe in subsequent talks we'll introduce some techniques and tools that can allow you to do that. So the sources for this, you can go read Smale's original work. I actually have never looked at it, so I don't know how hard it is to read. Everyone's favorite source is Milnor for absolutely everything. He has a set of notes. I think it's just called like lecture notes on the h-Cobordism theorem. It's a really nice exposition. Gives a very brief introduction to Morse theory as well. And if you want to go like super hardcore intense into Morse theory, his book is also a good place to start for that. Milnor has a book on Morse theory. It goes pretty extensively into it, like much farther than just the basics that you need for the h-Cobordism theorem. So we're going to use a little bit of Morse theory, but it's not going to be very intense. And it's the most differential geometry part of the talk, and hence it's the one I'm least comfortable with. I'm kind of pushing it to the end. Some other sources. This is one that's really good. I have a copy here. It's called Differential Manifolds by Kaczynski. It's sort of like a okay introduction to surgery theory itself. And something that's really cute about it is it has this picture in it of like every famous differential topologist of the 1960s, except for I don't think Novikov is there because of the Cold War. But Kervaire, Milnor, Chern, Hirsch, Whitney, Morse, Adams, Smale, Browder.
What was this for?
This was a 1963 symposium in honor of Marston Morse, the Morse theory guy.
Wow.
It's at the Institute for Advanced Study. So yeah, I can pass that one around. People can have a look if they want. And then there's another one that's kind of fun. It's called The Wild World of Four Manifolds by Alexandre Scorpin. This was where I first encountered the h-Cobordism theorem. They have a really nice overview, and they have really nice pictures in it. It's a really cute book, which is ironic because the h-Cobordism theorem isn't true in dimension 4, even though it's a book entirely about four manifolds. But like the tools that they give you, or many of them also apply to dimension 4. There's just one or two little details of the proof that don't work out.
So do you have like an idea of cobordism before?
Yeah,
like an analogous.
Yeah, I mean, like you can talk about cobordism all you want. It's just that this theorem about h-Cobordism theorems,
okay.
yeah, it doesn't hold in dimension 4. But there's nothing stopping you from talking about cobordisms in dimension 4. Nothing dimensional restriction on that. But in order to get this like nice criteria, you have to be in so-called high dimensions, which is dimension 5 and higher. So we're going to get to that. So we're going to start out at the basics, which is just what is a cobordism? What are we actually talking about here? And this is kind of a for fun talk. It's not going to be extremely rigorous. People in the comments like to call me out if I make mistakes, and so for anyone watching at home, please like and subscribe to the YouTube channel and add as many comments as you want. I'm going to make mistakes, so knock yourself out. So one caveat is we're not going to talk about corners. There's a notion of manifold with corners, which is kind of popular these days to talk about like extended quantum field theories. Back in the 60s, people didn't really care about corners. Wherever corners showed up, they would always have an argument that says you can smooth these corners. So whenever we have somewhere where we're introducing corners, I'm always going to say, smooth out the corners. Don't worry about it. Okay.
And there's also a canonical way of doing it as well, right?
Yeah. It's like up to diffeomorphism. Yeah, there's kind of like one way of smoothing out the corners. Yeah. So let's start with two closed, so compact without boundary, smooth manifolds. So h-Cobordism so I'm going to denote it with a W and then colon. So W kind of witnesses this relation between M and N, is a smooth manifold of one dimension higher. So that the boundary of W is diffeomorphic to the disjoint union of these two manifolds. So the picture everyone loves to draw is a pair of pants. Suppose this circle denotes M. Suppose this pair of circles denotes N. And a cobordism, an example of a cobordism could be something like this. Just make a pair of pants out of it. So obviously, a cobordism isn't unique. You can do lots of things. You can add topology to your cobordism on the inside. Maybe put like a little donut hole there. This is the picture of a cobordism that you want to keep in mind at all times.
Do you have like a classification of possible cobordisms that you can create between two things, or is it just always assumed that you can make it like it's you can do whatever you want?
I mean, yeah, sometimes two manifolds aren't cobordant. But if they are cobordant, yeah, somebody might have thought about that, like what are all possible homotopy types of cobordism between them. But like I said, you can always just keep like adding more and more.
Yeah,
rules.
exactly. That's why I thought maybe it's possibly infinite. Like it doesn't even.
Yeah, there's no limit to like the genus of the cobordism between two things. A harder problem is like if these holes are there, can you modify your cobordism to get rid of them? That's like a much less trivial thing. So that's what surgery theory is all about. So we probably are going to get to that sometime in the distant future. Not next week. Okay. So this is the basic picture. You can also throw in orientations. So let's suppose W is oriented. So i.e., what does that mean intuitively? We have a continuous choice. Of orientations for tangent spaces at points in P. So P and W. So what is an orientation of a vector space? Recall this is an ordered basis. Basis modulo orientation, so special linear transformations. These are the transformations that we think of as being orientation preserving. So in order to specify a basis for a fiber, it's enough to specify, in order to specify an orientation for a fiber, it's enough to specify an ordered basis. So if we have...
when you say a continuous choice, that just means like across all points.
Mm-hmm.
Okay.
Mm-hmm. So one thing you could do is you can take your tangent bundle and replace it with the determinant line bundle, and you're asking if that has a non-zero section. Yeah. That's an equivalent way of thinking about it, if that's something you're familiar with. Otherwise, you can just think about it as kind of frames, but modulo being able to rotate and swap two directions at the same time in order to do like two orientations reversing to make an orientation preserving. So it's just, if you think about it in terms of ordered basis, so W induces an orientation on its boundary. But not really canonically, you have to make a choice of convention. Picture. So suppose like W extends out this way. Here's your M. So in differential topology, you have a collared neighborhood theorem that says that if you have the boundary of a smooth manifold, then its normal bundle is trivial. And you can, in fact, the tubular neighborhood of its normal bundle is actually this little collar that sticks into the manifold. Gives a little trivialization so that, near the boundary, the manifold W just looks like M cross the interval, or wherever. I'll just write boundary W across the interval. So if you have a point on the boundary, and we've chosen an orientation for W, that means that at this point, we have some choice of ordered basis. So we have the ordered basis pointing, you can kind of orthogonalize to choose an ordered basis so that most of the directions are pointing in the boundary, and the last direction, or the first direction, is pointing into or out of the manifold. So by making various choices of convention about whether you want the orientation on the manifold to define an orientation on the boundary using an inward pointing or an outward pointing normal vector, this is a choice of convention that you have to make, and we're going to choose an inward pointing normal vector. So this is kind of like a hard thing to get used to, but I'm just trying to nail home the idea that an oriented manifold induces an orientation on the boundary, as long as you fix some convention about how an ordered basis at this point of W gives you an ordered basis for the directions pointing along the boundary. You have to really think about what you want that normal direction to be doing. What is it supposed to tell you? So if we have an oriented manifold M, and we want to talk about an oriented cobordism between M and N, the idea is that we want M and N to be on opposite ends of W. So that the manifold on this side, when you embed M into W, you want like the inward pointing normal vector to determine the orientation. And when you embed the other end into W, you want that W is inducing the opposite orientation. So if you take the orientation for your manifold N, and now you add the outward pointing normal vector, that's supposed to give you a positive orientation for W. And so this is supposed to be like, so this side of the manifold would be M, and then this side of the manifold would be N, and then I draw a bar over it to denote opposite orientation. So that, I mean, this is all kind of confusing, but
it still preserves the direction along the boundary, right?
yeah.
Like it only swaps the normal, the outward or inward, not the one along the boundary, right?
Yeah.
Okay.
Yeah. So like by taking like this way instead, what am I trying to say here? So like if we oriented this, the idea is that you have N embedded into this manifold, so that if you used the inward pointing convention to orient N, then you would get the opposite orientation of the one that you're thinking.
Yeah.
So this is kind of the idea, so that you have an M coming in and then an N is coming out. So oriented cobordism between M and N. So these come with chosen orientations already. So this should be a cobordism like this. Sometimes I write an arrow, sometimes I don't. So that when you take the boundary of W, oriented using whatever our fixed convention is, this should be isomorphic as an oriented manifold to M disjoint union N with the opposite orientation. So you're supposed to be thinking about like Stokes' theorem, about the fundamental theorem of calculus in particular. So one end of your interval is given a positive sign, and the other end of your interval is given a negative sign. This is the same kind of orientation concern with the
It might not be clicking in my head. Like it makes sense, but then when you wrote down the chosen orientations, suppose M and N have the same orientation.
what does that mean?
Like they both. Oh, I know that ends up working out. Oh, wait, never mind. Because it's all about the orientation that W induces when you kind of glue them together.
Yeah.
Okay.
Yeah. So in start out with manifolds that have their own orientation ambient,
Yeah, yeah.
and you embed them into W, then you can ask whether W is inducing the same orientation
Yeah.
or the opposite.
Yeah.
All right. This is an oriented cobordism. And then we just jump right into an h-Cobordism. I'll probably just add that right underneath. And yeah, if I'm trying to be clear, I would normally put like a subscript SO, like special orthogonal group, because they're orientation preserving. But since we're basically going to only be talking about oriented stuff, I'm probably not going to bother with the subgroup. Like, I'm never going to have to distinguish it from an unoriented cobordism, because everything's going to be oriented. Okay, so now an h-Cobordism is oriented cobordism. So a W going from M, SO to N, so that W deformation-retracts. Well, let's say it like this instead. So that the embeddings M and N embed into W as boundary components. So topologically, these should be homotopy equivalences. So in particular, an example of something that's not an h-Cobordism is this one that we draw way over here, as this little like donut hole in it. So for one point, like this boundary end has two connected components, but the whole manifold only has one connected component. So that inclusion of that boundary is certainly not an h-Cobordism. But if we just have like a cylinder between two ends, and then you add in a donut hole in the middle, that's also not an h-Cobordism because it has additional topology that the other ends don't have. So like an h-Cobordism is kind of like a really, like I like to draw like a wavy cylinder. So here's your M. And then you have some strange thing moving over to an N, where there's no topology in the middle, but there just might be some smooth weirdness coming from the smooth structure. Okay? So can I state the theorem yet? So, okay. Sure. Theorem, this is the h-Cobordism theorem. So let M N be closed oriented to manifold and comma W sure. So for an h-Cobordism, I'll put a little h there. So let's let W be an h-Cobordism. Okay, so M, and hence W, and hence N, is simply connected. Because if two manifolds are at the end of an h-Cobordism theorem, then they're automatically homotopy equivalent, because you can just compose the two homotopy equivalences. M is simply connected, and N is at least 5. This is what I said about high dimensions. Then your h-Cobordism, your wobbly cylinder, is diffeomorphic to an actual cylinder. So it's smoothly equivalent to a cylinder. And also in such a way that, well, M is embedding into the usual cylinder, and it's also embedding into the wavy cylinder. And so this diffeomorphism can be chosen to fix M. So we have the usual embedding as a boundary component. Here we have the embedding as the zero boundary component of the cylinder. So, yeah, our W is diffeomorphic to a standard cylinder in a way that leaves the M end unchanged. So just by comparing boundary components, right, the other end of the cylinder is N. That has no choice but to go to the other end of the actual cylinder. So in particular, as a corollary of this, you get that N itself is diffeomorphic. So this is your check to help you determine that two manifolds are diffeomorphic. And it's a little bit, the point is that it's a little easier than just sitting down and writing diffeomorphism going from end to end. You just have to find that they're on both ends of some larger manifold, and then check that your larger manifold has this topological property. This topological property, in light of the fact that M is simply connected, turns out that to check homotopy equivalence, you only have to do a homology calculation. So this turns out to be a very easy, relatively speaking, easy thing to check.
Do you want to dare question what happens in less than 5? I think I know you said some part of the theorem doesn't work, but which part and why?
It's called the Whitney trick, and the reason is that you can't always embed a disk into four-dimensional space. You can always embed it into
Five and above.
So are there examples in lower dimensions, lower than 5 dimensions, where this theorem doesn't hold them?
Yeah, I didn't go find any because they're actually hard to come up with. It would only happen in dimension 4 though. So there are kind of examples in dimension 4. So in dimension 3, 2, and 1, the h-Cobordism theorem is true, but it follows from like known classification theories, so the proof doesn't work. But it is true in those lower degrees. But the theorem is false in dimension 4. 4 is crazy. So in every dimension except for 4, we know there's a unique smooth structure on Euclidean space. In dimension 4, there's at least uncountably, like at least continuing many. So 4 is weird. We don't know if there are exotic spheres in dimension 4. We don't know. We've counted them in all other dimensions, and in dimension 4 we don't know.
Don't we know that it's like infinite, or is that also not, or is that also like unknown?
Yeah, unless I'm out of the loop, like
I don't know. Yeah, I
actually
could be
don't
thinking
know.
of something else, but I could have sworn that maybe it wasn't exotic spheres. Maybe it was something else.
Probably like real space. R4 has like continuum and smooth structure.
Okay, I mean maybe that.
Yeah, but like as far as I know,
Into that.
we actually don't know about spheres.
But we know it's at least continuum.
For the R4,
For-
it's at least continuum. Chaud's came up with the one parameter family of smooth structures. R4.
But we don't know it's exactly continuum.
Yeah, I don't think so.
Okay.
And then maybe not. Maybe because like the cardinality itself is continuum. I don't know.
I've heard continuum, but it could be just the speaker was being unrigorous. Maybe it's at least continuum. I don't know.
Yeah, I'm trying to be pedantic, even though like I'm making a billion mistakes.
What was the motivation? Like you said that this allowed us to really start studying before the exotic spheres
Mhm.
or whatever, but was that the motivation for h-Cobordism theorem, or was there something else, or was it kind of a PMAT thing where they fiddled with it and then it ended up becoming useful?
Yeah, I'm not fully sure like
Okay.
what exactly is the motivation or how someone would have stumbled across this. In the 1960s and 50s, like everyone was putting everything they could into understanding like the differential topology and how algebra comes in, algebraic invariance. This could very well just be like the natural result of like dozens of people thinking about stuff like this.
Okay.
Smale just kind of put it all
Yeah.
together.
That was just great.
Yeah.
The original exotic spheres were 7-dimensional?
Yes, the first one that Milnor found was 7 and then Kervaire and Milnor later came up with a more systematic process of producing two-body space. So Milnor's original thing was kind of ad hoc, and I think like the one he came up with generates a group of order 7 or something like that, but the group of homotopy spheres into dimension 7 has 28 elements. So they had to do like a little bit more work to find like the actual.
Another way of doing it, I think I was talking to you about it, was recognizing as a S3 fiber over S4, and then
These are classified for you. Let's see.
yes,
And then come up with
You-
the lambda invariant parameters.
Yeah.
Classification. Yeah,
Yeah.
we can also do that. Yeah, that's like Milnor's original thing.
Right.
Something about it along those lines.
And yeah, you get pi 3 of SO3. 4?
The SO4.
SO4.
SO4 adds some issues.
Right, yes, you're right. Pi 3 of SO4.
And that's Z plus E.
Yep, exactly.
Turns out.
Yeah.
Happens to be Z plus E.
Yeah.
Okay, so here's the theorem. Okay. So, like I said, I did mention one thing, and I'm going to write it down because it's essential thing that we need to know. Here's the fact. So if what we have there, n is simply connected, and so if you have an h-Cobordism, this means that W is simply connected and n is simply connected. Well, then, actually no. Let's just suppose n is simply connected. So then to check, let's assume m and W. So if we know that they are simply connected, then to check that the inclusion is a homotopy equivalence, suffices to just compute a relative homology group, H star Wm, and see that they're equal to 0. This is way easier than coming up with a homotopy inverse. We just have to compute homology. I'm going to look at my notes and see if I wrote down a sketch of an argument there. Yeah. I can say some words about why this is true. Try not to emphasize it too much. It is like a little bit of technical algebraic topology here. What was I saying? So proof sketch. So because M and W are manifolds, we're going to see later, in fact, that manifolds admit CW structures, so we can just treat them as if they're CW complexes. So we have M embedding into W is a homotopy equivalence if and only if the mapping cone, W union the cone on M, is contracted. So what does that look like? Here's your W. M. So mapping cone, embedding of M, you're basically just attaching a cone. Manifold, it's not a manifold anymore, but you're essentially just taking this M part and forcing it to be contractible by adding a cone at the end. So if the inclusion of M is a homotopy equivalence, that means we must be able to take the rest of this manifold and kind of retract it onto this end, which then contracts down to a point. So their homotopy equivalence, this embedding, is essentially saying there's no additional topology in the rest of this cobordism. And it's all just contained in this M part and coned off. But the other way around, it's kind of a similar argument.
Why did we?
Next part of it, so when you go and actually compute this relative homology group, since this is a quote-unquote good pair, this is the same as the reduced homology of the quotient, which is by homology stuff. The quotient is going to be homotopy equivalent to this mapping cone. And so since we know that the mapping cone is contractible, that's going to tell us that these groups are all good. So, okay, good start. Moving this in the right direction. So if X is simply connected. Sure. So if we have that this is a homotopy equivalence, then this is true. So if we're going the other way around, we know that this is true. Yeah. If we know that this is true, now we want to deduce that the homotopy groups, so that starts here, that the homotopy groups, W, mapping cone, all to M. And the way that we do that is the Ravitch theorem. I won't say anything about this because I'm never going to read it, need it for the rest of the talk. I'm going to mention that it's being used. It's a non-trivial theorem. I encourage you to look it up. And then once we know that the homotopy groups vanish, then we can deduce the homotopy equivalence using Whitehead's theorem, because it's a CW. So again, this is like some technical algebraic topology. They're kind of difficult results if you've never seen them before, but at the end of the day, they're also very basic because they're from like pre-1950s. I'm just writing them down. Hopefully you will look them up. But this is I just wanted to give some justification for why I get to only think about homology when I keep talking about sort of like homotopy equivalence and stuff. In general, you can't just compute homology to determine a homotopy equivalence, but you can when all of this stuff is a CW complex and when everything is simply connected. So that's the principle to reduce it to thinking about homology. So we're going to be working with these homology groups in order to actually prove the h-Cobordism theorem. So I had a corollary, but I'm going to just do at the end. Okay, so that's the setup. This is the h-Cobordism theorem. These are the basic objects we're working with. This is just like a hand-wavy justification. Anyone have anything that like to ask about more before I outline the proof?
So I guess that this says that there's no such thing as an h-Cobordism between two manifolds, only one of which is.
Yeah, because if the just by definition of h-Cobordism, because if the other one wasn't simply connected, then they're not going to be homotopy.
Yeah. So can you keep going with like the homotopy groups like for manifolds that are not simply connected? Will there be no such thing as h-Cobordism between those?
You can have manifolds that aren't simply connected and have an h-Cobordism between them.
And like anything groups, they have to be like not simply connected the same way.
Yeah. So they wouldn't have to have isomorphic homotopy. Yeah, because the point, the one conclusion about if you know they're existing h-Cobordism theorem between two manifolds, then you know they have to be homotopy equivalent. So like because like the inclusion of either of the boundaries is a homotopy equivalence. So you can just like choose a homotopy equivalent back here and compose like that. So in particular, they would have to have isomorphic homotopy groups all the. You can definitely check in advance to see that there is no h-Cobordism because like your homotopy is very different. Okay. Yeah, so having an h-Cobordism theorem obviously, having an h-Cobordism is obviously a strong condition because the reduction you need to make is extremely strong. You actually get the picture more. Even though like this doesn't count, when they're not simply connected because the proof doesn't work, but yeah, just the existence of the h-Cobordism alone is already a strong condition related to these two manifolds together. Okay. So here's a proof outline. And then I'll outline the proof, and then I'll try to cover it as much as I can. Mostly just when we'll be talking about handles. So, the first step, the manifolds has the handle decombination, which I haven't talked about yet, so I have to leave the quotation marks for now. We'll get to this, don't worry, we'll get to this. So roughly what this means is that M is diffeomorphic to a union of a bunch of k ranges over the possible dimension. And then in each dimension you have a collection of handles, which I'll call H, A, I, where a handle looks like this. This dimension k, and then you thicken it up with the complementary dimension, so that in total the dimension is equal to m. And so, for example, do the one handle. One handle is 3, so this is a D1 plus D2. So it's a solid thing, solid product. And for example, here's a 2 handle, actually like the exact same manifold, but you're looking at it from a different perspective. D2 plus D1. So the idea with the handles is, we're going to see this in a bit, the boundary has these 2 components. There's the boundary component of your leading disk, and then there's the boundary coming from your upper disk. So we're going to think of the first part of the disk, the leading disk, as being like the geometrically interesting stuff, and the rest of the disk is just thickening it out. So when we attach this to something, we're going to take like the sphere of your leading disk and glue that on the stuff. So the picture that you're going to see, I'm going to draw it now to make sure I don't forget. We went into like the office of the world's leading surgery theory guy and asked him what a handle attachment looks like. They are going to draw this picture. Every single one of them is going to draw a suitcase. So this is a 1 handle that's been attached onto a manifold with boundary. And I'm thinking of this manifold with boundary. I'm thinking the bottom and the top lines are the boundary, and that the vertical lines are just there for like emphasis, I guess. And so we're attaching a 1 handle onto the top boundary. And so you notice, like, of course you change the topology of the manifold itself, but also the manifold boundary at the top, the topology changes in such a way that you like remove some sphere across a disk, and you glue in some complementary sphere across the disk. So the effect of handle attachment is, I'll just mention it now because I don't think I'm going to need it at all for the rest of the talk. Handle attachment, this is something that happens like the ambient, so the ambient dimension is everything, n, n manifold. This results in a surgery. Well, the surgery theory is all about the n-1 dimensional boundary. So the existence of handle decompositions for a manifold, and then essentially just boils down to saying that you can start with like one of your boundary components of the manifold, and then just do a bunch of surgeries to it in order to get to the other boundary. I'll spell that out more when we actually get to it. Just want to show some pictures. And so how do we know the manifolds emit handle decompositions? This is where Morse theory comes in. This is the technical analytic result that assures us that any smooth manifold is going to have some handle.
It's probably a really weird question. But, like, we already know if it truly is like a handle, it's just a thing made up from a disk, right? If I'm just thinking about it like that, doesn't it also just follow from the fact that you can, like, thicken up the open charts that cover a manifold? Or is that not, like, viable?
No, not really.
Okay.
Yeah, I
I'm just
mean,
curious
like,
why we
open-
needed, like, a whole new, or why we need Morse theory to prove this.
Like the open charts in the manifold are already like maximum thick. So an open subset of a smooth manifold is a smooth manifold with the same dimension already.
Oh, yeah, that's true. Yeah, I just can't really picture how it looks like. Like a handle decomposition, I mean. Like, I know what the handles look like, right? And how they kind of, like that canonical example is a suitcase, but
Okay. Let's see.
if you have, like, an example or...
Yeah, we can get to it later.
Oh, okay, then yeah, don't worry.
Okay. I can just skip ahead to it now. Yeah, I'll wait until I introduce a little more language.
Yeah, that's fine.
Okay.
Can all of these be written nicely using the boundary connected sum?
Nope.
Nope.
No, that's a very particular example of a handle. So that's the first step, is just ensuring that manifolds have handle decomposition. Next insight comes from seeing that a handle decomp a Cobordism or Cobordism. For our purposes, those words are going to mean the same thing, so I'm sure I'm going to slip and write Cobordism all the time. Because of the Cobordism, write W from M to N, gives us a chain complex called the handle complex, and it computes our homology group. So this is the thing that so because everything in sight is simply connected, the thing that we're really interested in that determines homotopy equivalence between the Cobordism and the end, this thing is computed using our really nice, handy handle decomposition. So the assumption that we're going to use, which is that this is 0, is going to put, so the vanishing of these groups, here, puts a strong condition on our handle decomposition itself. So this is where the algebra and the geometry start to interplay. It's the fact that we have this homotopy invariant, that the assumption of our theorems is telling us is 0, and it's computed using this kind of rigid, or at least more rigid, handle decomposition. And so the way that the handles all attach together, that's the thing giving us the boundary for the chain complex. And so the fact that this chain complex is exact gives us a lot of information about the way that our handles are attached. And we're going to be able to leverage that in order to clean the handles out. So for example, I guess that segues right into this. So handle complex is exact. So what this means algebraically is that there's a basis for it over Z. So the boundary maps take the following form. So either have a bunch of 1s there, followed by a bunch of 0s, or you have a rectangular matrix that's full rank top, and a bunch of 0s underneath. So these 1s, so if this is like the boundary operator going from the k chain group to the k minus first chain group, this is saying that like all of these k handles get paired up precisely with some k minus 1 handle, and then all of the k handles coming from over here, those just all go to 0. Exactness means that going to 0, that means I had to come from something in k plus 1. And so this is going to pair up, so this pairs up algebraically all of our handles. Then, the tricky part is, okay, so all of our handles are sort of paired up algebraically. We want to try to use that information to cancel out paired handles. Actually, so changing basis is accompanied by a geometric handle use. So that when you actually change your chain complex to have the basis describing our boundary maps like this, when you make that algebraic change of basis, there's also some geometric moves that you can do to move handles around so that your actual handle complex is giving you this chain complex. So it's not just a formal algebraic thing, you actually do a geometric change of basis. accompanied by geometric. The term that everyone uses is handle moves. So there's handle cancellations and handle slides. I'm probably going to talk more about cancellations and slides. Okay. Yeah. So we want to cancel paired off handles. So I'll show you what I mean by canceling handles. So suppose that we start. This is a picture of a zero handle, three-dimensional manifold. It's going to be a D3, it's going to be a D0 cross D3. So you can come along so that there's a boundary at the top. Right? So you can come along and attach one handle to it, one handle attached to it. Now we can come along and attach a two handle to this. So remember, the two handle looks like a thickened like a hockey puck. Oh, I got almost got. Okay. Here's what the picture's kind of looking like here. So let's say this piece of paper is a one handle, and I'm like attaching it to the desk like this. So I've introduced some new topology to the desk. And then this hat, with its like thickening, is a two handle. So I can come along to this one handle I've already attached, and like attach my hat to it, so that I've really just made like a cage. So you can see that like you can kind of deformation retract the one handle over the hat, or in chalk dust now, to actually like flatten it back out. So in pictures, so it would look kind of like this. We've got one handle attached to what would be a manifold, and then we just come along with like a two handle, reversing the one handle, going underneath, it's thickened, right? So we just fill in this hole. That goes behind. Now this is just a solid chunk of manifold, and you can just push it down to get back to a manifold that didn't have any handles attached to begin with. So this is a picture of what handle cancellation looks like. So these are like diffeomorphic. So we want to be able to cancel off these paired handles, and there's like an obstruction to doing that. So another picture in one dimension might be like, here's two, so the idea is essentially every handle has kind of a midway sphere, which is going to get called a belt sphere when I actually start drawing pictures. And our other sphere that we're gluing on along the attaching sphere, if our attaching sphere of one of our handles crosses the belt sphere of another one, that means that these two things are like algebraically connected through the boundary map, and I'll make that more explicit in a bit. So we're imagining this is like an attaching sphere of one of our handles, and this is like this midway belt sphere here. And suppose like our intersections come with signs depending on how the orientations match up. So in this picture, we can just take this guy and push it down, so that the intersection is reduced. And the question is, can we always just do that? Can we always just take like a pair of intersecting points with opposite signs and just eliminate those 2 points? And so like as long as we only cross this belt sphere exactly one time and we don't interact with any other handles, that's actually a sufficient criteria for being able to cancel those 2 handles out. So in this picture, it's not clear whether we can or not because it intersects 3 times. But by some geometric argument, we can actually separate them so that it does. It's possible that you have some weird topology, like maybe your one thing goes up here into some strange stuff, and then comes back into some other strange stuff, and then keep going, right? So depending on how weird these regions are, maybe you can't geometrically cancel these 2 points out. So you need to have some careful analysis to make it work. And the thing that makes it work, if 2 things, boundary is simply connected. So the boundary W is simply connected. Well, no, I will just say M. So like a component of the boundary. M is simply connected, and if n is greater than or equal to 5, then we can use the Whitney trick, which I'll talk about. So this is named for Hassler-Whitney, who also did the Whitney embedding theorem, and also was the Stiefel-Whitney class guy. He was a very big component of differential topology leading up to the 1930s. His main stuff was like in the 30s and 40s. So he's kind of drawing that into this stuff. Okay, so that's the outline of the proof. I'll go over it again because that was kind of a lot to take in. So the first thing we do is we get out of nowhere from magic of Morse theory a handle decomposition. And then we say, okay, our handle decomposition computes this relative homology. That's great. From the assumption of the theorem, we know that this relative homology group vanishes. And so by doing algebra, and I'm not actually going to elaborate on the algebra, I'm just going to do this as a black box. By doing algebra, we can change a basis of our homology, of our chain complexes rather, so that all of our boundary maps take on an extremely simple form that pairs up all of our handles in our handle complex. This change of basis is actually implemented geometrically by making small alterations in our handle complex. And these alterations give us what's called an algebraic intersection number of 1. So these two lines have algebraic intersection 1, and the challenge for the rest of the proof is to make this algebraic intersection equal to the geometric. I want to cancel off geometrically these algebraically canceling points. So once you can do that, then you can cancel off all of the handles using the Whitney trick. And then once our handle complex has no handles, our handle decomposition has no handles, it must be a cylinder, which is nothing happening. So that's the outline. So I'm just going to start now to talk about if handles.
Just that last sentence. If there's no handles, it's a cylinder.
Yeah. So, so the way that the handle decomposition actually works is you start with a component of the boundary, say M, and you take the cylinder off. Okay? And then you build your manifold by attaching handles to that. In some way, blah, 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 blah. So if your handle decomposition,
You build W out of it.
yeah,
Okay,
starting
yeah.
from the cylinder,
Starting from, yeah.
you build W.
Okay.
And so then at the end of the day, we're like, okay, well, you've eliminated all our handles. You just have a cylinder, you haven't done anything.
Right, so, yeah, okay.
So that's the idea.
Sorry if it sounds like a master garbage, but
No.
picture it.
This is fine. You haven't done master's degree of human so this isn't like, okay, so we're going to jump into handles and handle decompositions. Now is a great time if you have further questions. All right. Okay. Like I said, what is a handle? And N is a smooth N manifold. Looks like it shows in diffeomorphic. Smooth product. This is a K. Maybe it's N.
Yeah, no, you wrote it.
Yeah, oh yeah. Yeah, K handle in ambience n. So n is kind of the ambient dimension. So it's a little bit weird sometimes because like half the time our ambience is going to be n plus 1 if you're thinking about that using but this, I'll just state this definition for n. Yeah, that's all it is. And we're going to draw a picture in order to identify the key region for the n. So, like I said, the interesting geometric dimension is the dk part. So I think we'll draw that in green. So this is the dk part of our case. So we call that core. And so then we want to attach this thing to another manifold by gluing the two ends on. And so I'm going to indicate this attaching region, well as like the center of this area. So this is called the attaching the attaching sphere is going to be the boundary of our core. So that's going to be sk minus 1. And then, yeah, it's the sk minus 1 cross 0. Right, and this is equal to the boundary of the core. And then, but we don't just want to attach at the sphere, we want to attach along the entire thickened attaching sphere, which I will call the attaching region. Topologically, it's the sphere that's important. So sk minus 1 cross the complementary disk. Then, like I said, there's kind of something dual to the attaching sphere. And that's this midway thing, which I will call the belt sphere. It's a very common usage thing, a belt sphere. Like I said, this is dual to the attaching sphere. This is going to be a 0 cross complementary sphere, which is S n minus K minus 1. This is kind of your like anatomy of a handle. So the attaching sphere and the belt sphere are going to be the important parts for us to talk about like the topology of attaching one handle to another handle. How to actually construct the chain complex out of these things. I'll draw another example of the two handle just to see like how things work slightly differently on another handle. In fact, I'll draw the 0 handle and the 3 handle as well because there's important things to emphasize about both of those cases. So this is a 1 handle. 1 handle. 3. It's okay. Click on that. Yeah. So let's try a 0 handle. So this is going to be a E0. E3. Well, so the core is just going to be the central point. Here's our disk. Core is going to be the epicenter, right? The attaching sphere and the attaching region, right? S minus 1 is the empty set. So both of those are actually just empty. And it's the belt sphere that we find on the entire boundary. Belt sphere is the boundary, and the core is still sitting there. So a 0 handle, there's no attaching sphere, no attaching region. So when you attach a 0 handle, all you're really doing is just putting it there. You're just taking a disjoint unit with this. So you can attach, attach 0 handle to the empty handle. That's really important. So when you're building up the handle decomposition from nothing, you have to start with 0. Okay, and the dual picture, extreme opposite end, the 3 handle. Now the belt sphere is 0. You can't attach it to the 3 handle. So it's the same, it's topologically also just 3-dimensional this, but the spheres are arranged differently. Okay, so what is the attaching sphere? It's just S3 cross 0. Yeah. Yeah, D0 is the singular point 0. So in fact, the attaching sphere and the attaching region are the same. And it's just the boundary. And the core is everything. So the core is everything, like the solid sphere. I don't know how to really draw this. So the core is everything. The attaching sphere equal to the attaching region. Does that describe how to actually attach spheres? Yep. Maybe we'll get to that. And then finally, I just want to draw 2 now. So like I said, this is like a hockey puck picture. So what would the core be? So this is D2 cross 1. So the 2-dimensional part is your median thing. So the core is going to be the disk that's in the middle here. That whole disk is the core. Going through the middle of this hockey puck. Attaching sphere was the boundary of the core. This part here. The attaching region was everything thickened up. So that's the entire boundary of the puck. So when I was doing the thing with my hat, the rim part of the hat, that was the attaching sphere. Good. And then finally, the belt sphere. Belt sphere is going to give us the 0 sphere. So that's just going to be the midpoint of the top disk and the midpoint of the bottom. So I'm going to belabor that. I really wanted to make sure that these pictures are very clear. People know what all of these anatomic proportions are. Okay. Now we're going to go, what does it actually mean to attach a hand? This is just the classical topological construction. You just choose an embedding part of a space into another space, or rather you can choose an embedding of one space into 2 spaces, and then glue those 2 spaces together along this common subspace. So that's what a handle attachment is in principle. So let's let, say, W n plus 1 manifold with boundary to be empty, or let's just say it at 9. So then choose embedding so it's going to go from the attaching region of the case here. So that's full complementary disk. Now, like I said, the stupid ambience thing. So over there, my ambience is n, and over here, my ambience is n plus 1. I think I'll keep it like this so it's less. So now we have an n manifold with some boundary. So we're going to choose an embedding of the attaching region of a handle. That's the attaching region. I don't think so. This is the embedding of the attaching region into the boundary. And then we define the symbol. We're going to draw a chi. And the manifold we're attaching it to. And then the embedding, this is going to be our k handle, dk cross n minus k. disjoint union with W over phi. No, yeah, this is the notation we're going to use. We're going to take a union over phi. And what this is actually defined to be is if you take a disjoint union of these two spaces, and you take modulo P comma B is identified with phi P comma B for all pairs PD in the attachment region. So I'm going to draw the picture again. Right here already. Here's our W. Here's our one handle. I'm going to write it as a K handle. And so our attaching map, you're going from the ends of your handle, and you're embedding it into this boundary component of W, and then this, what's called a trace of this handle attachment, or trace of the surgery, is just what you get when you identify this region with that region, and this region with that region. So by attaching the handle, you just recover our suitcase. This is the picture of the handle attachment.
Can you provide, but given that you use the variable phi, pi, and just use the word trace, is there any relation to the character for this stuff or not? Yeah. Just consider using pi instead of with trace.
Yeah, no, I don't know. I don't think so. It's just kind of the typical, it's just like the classic language that topologists use for like the trace of the surgery, or even like the trace of a homotope is something that people like to use. Okay, so let's look at a great example. It's okay. It's too general. Let's look at something more specific. Example, let's start with W is an empty manifold, and let's declare it to be two-dimensional. So we can attach a zero handle. Because the attaching region of the zero handle is empty. That's the best embedding anyone's ever thought of.
Awesome. Yeah.
So then chi of our W at phi 0, this is just a disk. So this time it's not solid, it's just a two-dimensional disk, which is cupped. And the belt sphere of this thing. Now the belt sphere of this disk is all of this. Okay. So then we're going to come across and take a one handle. Come along and take a one handle. And draw like this. Suddenly forgot how to draw it. So we come along with the one handle now, and we can choose our attaching map like this. So this is my schematic drawing for phi 1, right? It's going from S0 cross D1. So it should be D3. No, yeah. Ambience 2. Okay, and so if we do now two attachments in a row, what we get is this little like basket. Okay. So far so good. Now let's take another one handle. Draw this maybe. Hopefully you can see that. So we're going to take another one handle and attach it onto this one.
Like onto the basket handle that we get?
Yeah. So this is something I want to emphasize with this example is that you can just successfully attach handles onto handles that already exist. You don't have to like avoid the handles when you're coming up with the handle decomposition. So when we take our phi 2, right, it's another attaching map. then we're going to get something kind of strange. So how do I draw this? I draw it here. This.
Get an artist to do certain things.
Take down. This comes down. Down. So you can kind of see what it is. You take a handle with a basket and you put like another loop on the top. Now notice something interesting. If you squint real hard from far away, maybe you can see, you can trace along the boundary and find out that there's only one boundary component. So you can actually attach a tooth handle now. Attach along boundary. That's one boundary. When you do this, there should be a phi 2 here. Oh, this one's phi 3. You do that to yours. So like this part is this part, and then this part is like this part. It's not totally easy to see, but this procedure constructs for you a handle decomposition for the standard two parts. So we'll do an example of handle decomposition of something that we're already familiar with. Okay. So just as a technical definition, maybe I'll just say in words, save time. A handle decomposition for a smooth manifold is a diffeomorphism. So if you start with a smooth manifold that has a boundary component M, and this boundary component, again, it could be empty. Over here, we started with something empty. So a handle decomposition is a diffeomorphism between W and a sequence of handle attachments starting at the cylinder on this boundary component. So for some sequence of handle attachments. So very roughly sketched one for the chorus there. These are going to be the basic framework for like the entire h-Cobordism theorem proof.
Are there questions about this so far?
Okay. So you're starting to see maybe a little bit how the belt spheres and the attaching spheres kind of relate to one another. Where like when our attaching spheres hit a belt sphere, in particular when they can't be moved away from the belt sphere. That's when like interesting topological stuff is happening. So, we want to have a language where we can reasonably talk about how are the belt spheres and the attaching spheres intersecting each other, so that we can come up with a chain complex based on the handle decomposition. This language, which is extremely, extremely important in all of differential topology, is called transversality. So I will just define it, and we can go to pictures. So let n, dimension n, M, dimension M, Z, dimension Z, the smooth manifold. Let's let F from N, Z, G from M, Z be functions. So, F and G are transverse. Let's say if for every, let's say P, Q, and product with, so that F and G collide at these two points, every pair of points that collide under F and G, you must have like the push forward tangent spaces at those points. I'm going to say D, P, F of the tangent space of P and M plus G of the tangent space U greater than N should be equal to the tangent space of their common tangent. Easy. So it sounds weird. Let's look at examples. And there is a notation for it. With F, latex command is pitchfork.
That's the first.
So let's look at a couple pictures. So let's say the ambience Z is equal to R2. So the fun was just let these be aligned. So maybe this is the image of N. This is the image of M. Right, so wherever we have collisions, we want to check to see if the tangent spaces of these, in this case I've drawn them as submanifolds. In general, they don't actually have submanifolds. We want to know that all of the ambient directions at this point are covered in the image of N and the image of M. And so in the image of N, these are our tangent directions. In the image of M, these are our tangent directions. Those are linearly independent. And so we get the entire tangent space of R2 at this point. Similarly, there's the tangent directions for M, there's the tangent directions for N, linearly independent, so we get the entire tangent space at this point. This F and G are transverse. An example of the F and G that are not transverse is if they come and they just barely glance off of each other. In this case, in this case, both manifolds' tangent directions are collinear. So you only get that direction, you don't get anything else. So these two functions are not. So what? Okay, good question. Very good. It turns out, if we have two transverse functions, or two functions intersecting transversely, and two submanifolds that are intersecting transversely, intersection is also a submanifold. And the dimension of the submanifold is computable out of the three dimensions that you start with. So, big black box from differential topology, called the transverse intersection theorem. It's the absolute theoretical core of the conceptual homeomorphism. That work. So we have F, G, transverse, and the intersection is a smooth manifold. Dimension start with minus infinity. So in this case, 1 plus 1 minus 2 is 0. These things are intersecting in point. Let's try, we're in R3, right? Here's something two-dimensional, here's something one-dimensional. They add up to 3, they intersect at a point. Intersection. There's another two-dimensional thing. If we come along with another two-dimensional thing, 2 plus 2 is 4, minus 3 is 1, they intersect in the line. So all of the stuff we know about, solution spaces for linear equations and stuff like that is really just locally modeling the inverse intersection. You should be thinking about, subspaces of Euclidean space as a local picture for what this transversality stuff is. And really quick say transverse approximation. We'll be very imprecise here, just for the sake of time and boredom. Transverse approximation. Just going to say we can always nudge two functions or continuous functions. You can see this function be dense, in this case a continuous function. You can always nudge them to make them transverse. In fact, if they were already transverse over some open subset, over some closed subset of the domain, you can actually leave them fixed on that spot where they're already defined. So it's just wherever the functions are bad, you can just perturb them a slight amount to make them transverse. So in particular, all of our attaching maps and belt spheres and stuff like that, we're always going to just nudge them a little bit to always assume that the attaching sphere and the belt sphere are transverse. We're allowed to do like and subscribe to the YouTube channel. Please leave a comment. Okay, so the transverse intersection theorem is going to tell us a lot about how we actually attach handles. So the principle is handles can be attached in order of dimension or in order of degree f. Increasing. Meaning that if you have something that has like a K handle attached, and you come along with an L handle, where L is less than or equal to K, you can attach it in a way that completely avoids the K handle that is always there. You only have to be worried about things that have dimension smaller than the handle that you attach, or degree smaller than the handle that you attach. So why is this? Is it right here? Sure. Yeah. The principle of why is it important to separate things? So if the attachment sphere can make this joint on the belt sphere. Handle out there. Order to attach you doesn't matter. You could have attached this handle first handle, and then the other one. So this is the principle that we're trying to apply. So we're going to use transversality in order to determine, well, when can you do that and when can you not necessarily do that. So this is actually going to be like a little tougher. So we've got half an hour left. We definitely want to draw the looking trick. I'm not going to get to absolutely everything, but let's see what it is. Here we go. Suppose this is the annoying and changeaway ambience now. So suppose W n plus 1 is a manifold boundary. And suppose we have already A prime. So let's try to K handle the something. Attaching that is going to go phi from the attachment region. What did I say? Sk minus 1 plus and plus 1. Like that. Okay. So, topologically speaking, the attaching region, right, that just deformation retracts down to the attaching sphere. So topologically speaking, we only really care about the attaching sphere, right? So let's do a little analysis. So in the attaching sphere, for our K handle, remember, this is going to be equal to what the attaching sphere was. This is K minus 1. Yep. And then the belt sphere, our K prime handle, that we're trying to avoid. And so the belt sphere of the K prime handle is going to be an erasive gradient. So we have it's a mid-rank thing, so that this we're reading this as 0 coordinate. And then we're going to get S minus K. I'm subtracting off this one. We get an N minus K prime. These are the two dimensions. Let's add them together. K minus 1 plus N minus K prime. That is N minus K prime minus K minus 1. So, right, our ambience is N plus 1 dimensional, but we're actually attaching it to the boundary. Specifically, only attaching it to the boundary, which is N dimensional. So all of our handle calculations are done with N plus 1 ambience, but for the transversality principle, since we're attaching it only to the boundary, we want to think about having an N dimensional ambience. Just looking at the boundary of our N plus 1 dimension. So this, right, this should be less than N if and only if, right, K is less than K prime minus 1, which happens if and only if K is less than or equal to K prime. E, by the transversality property, if the handle which was already there, so if the handle that was already there has to be at least as large as the handle that we want to attach, then the order doesn't matter. So you can always attach the one which is smaller first. That was just a technical thing that we had to make sure of, that we can always just attach them in order, so that this is going to let us actually define a boundary operator on a chain complex. Because all of our K handles, we know that we can arrange so that they are attached onto all of our K minus 1. In particular, let's do another little calculation. So if we attach K plus 1 handle to a K handle, so what are the numbers? So i.e., I'm going to follow my notes because I'm going to i.e. k prime is equal to k minus 1. So then if we do our calculation again, add up the dimension of our attaching sphere and our belt sphere, we actually just get exactly equal to n. So therefore, transversality gives us a zero-dimensional intersection, i.e. a collection of points. Since everything's compact, you get finitely many points. So here's one place where compactness actually makes an appearance. You get finitely many points. So orientation gives us signs at those points. And we're going to define, kind of looks like an inner product. So the intersection of our k handle, I think we can do like this, with our k minus 1 handle is equal to the sum of the signs of these points. So this is looking like one of the drawings I had before. Here's one of our things. Here's another one of our things. That's plus, that's minus, that's plus. So the plus that we get at the end by canceling all of this stuff out, I'm denoting it using this bracket. So I don't have to describe it over.
And this notation has nothing to do with quantum mechanics.
I hope not. Really hope.
Don't bring your sick perversions into my sacred spaces.
I know for TQFTs the caps are actually your bras and kets. It's to get your field out of it.
Yeah.
Usually conflicts.
That is actually good.
Yeah.
Sure. Good comment. Okay. So now that we have this, let's actually define this chain group. So let's let W be a manifold handle decomposition. And again, we don't actually know that we can do that yet, but I'm assuring you by an independent amount of work later, Morse theory, we can always get a handle decomposition. And I'm going to do it like this, M cross I, M being one of the boundary components of W. And then I'm going to have a whole bunch of zero handles for some index set. And we have a whole bunch of one handles for some other index set, all the way up to a bunch of n plus 1 handles for other index set. So here's a big collection of handles for our manifold W. So now we're going to define C K to be the free abelian group on the collection of K handles. We're going to define a boundary operator going from K handles to K minus 1 handles, and it's going to take, I'll just denote, kind of being like loosey-goosey, talking about embeddings versus the actual geometric piece. So we're going to take a handle of degree K, and we're going to take it to sum over all K minus 1 handles. So in a bigger. And you take the incidence number, I forgot to mention, that's what it's called, is the incidence number in front of the handles. So like, you have a one handle here, this is maybe h1, 1. Another one handle here, h2, 2. And you come along with like an attaching map for a 2 handle, goes between the things and then comes back like this. So if this whole thing is a big 2 handle, like h2, then your boundary for h2, depending on your orientations, I guess you can probably just arrange your orientations to get the sum of these 2 lines. And like, if instead I'd gone something silly, like make the attaching map go twice around or something like that, there's no reason why you couldn't do that. Then the boundary, the incidence value would be 2 times. Right? It's tricky. This is the basic idea. It's not entirely clear that this is a chain complex, that if you do the boundary twice, you get 0. Tried thinking about it for a little bit, and it was not immediately obvious. And I decided not to think about it anymore. No, we're just giving the talk now. The difference is that there's a smaller amount of time in which I actually have to think about it. Yeah, so said, you do it twice in a row, you get 0, it's obvious.
Cool.
Yeah, it's got it. Probably. Okay. Yeah, wild rule of 4 manifolds doesn't actually work out a lot of stuff. It's just more like an exposition. Kaczynski actually tries to do the work.
Well, geometrically it's obvious. Algebraically it's not obvious, but
okay, so this gives a chain complex and we can take its homology. Handle homology W relative to M is going to define to be the homology of this chain complex. Kernel of the K boundary operator modulo the image of the K plus first boundary. So this condition says, of course, and if you haven't seen this stuff before, the image of the K plus first boundary operator is contained in the kernel. The K boundary operator, and the homology measures exactly what the difference is. So this is a definition, theorem, which you can kind of imagine should be true because all of these disks are just thickened cells. So the K handles are thickened free cells. So the handle homology of W relative to M, is actually just naturally isomorphic to the ordinary homology W relative to M. So, which you could compute using the CW complex or with the singular complex. Using the CW complex is the most direct way, I think, to see that these two are the same. So this is good. This is one of the big things I wanted to get to. 15 minutes left. I've already kind of talked about handle cancellation. I've already been really, really rough about everything, and I only have 15 minutes left, so I'm not going to formally talk about handle cancellation. Well, I should mention at least what the actual term says. So if you attach, consider, suppose we do a surgery or attach handles to some manifold W. We attach a K handle first, and then we attach a K plus 1 handle, so that the belt sphere, so that the attaching sphere, I meant to use this notation the whole time, but the attaching region of this handle, the attaching sphere of this handle, intersects the belt sphere of the handle that we already have in exactly one point.
Sorry, can you write your indices a bit bigger and more clearly?
This is the K handle. A plus 1 handle. Ones are the same, right? Careful. A handle. And this should have been. Oh,
No, K minus 1. Oh, sorry.
So if our attaching sphere, our K plus 1 handle, intersects the belt sphere of our K handle at exactly 1 point, so then our manifold with the handle is attached. Like I said before, you can kind of just scrunch it down. This is diffeomorphic to the manifold that we started. This is the principle of, like, if we have handles and we want to get rid of them, we need a lemma that says when we can actually drop them. And this is the lemma that says that. Cancellation of handles. So now this raises the issue that we had mentioned at the beginning. If you have points, like if your incidence number is 1. So what if we just have the incidence number is 1? So this isn't telling us that we intersect exactly once. It's telling us that we take all of our intersections and pair up pluses and minuses as much as we can, and we'll only be left with 1 point left. If we can geometrically cancel those pluses and minuses, then we can apply the handle cancellation theorem. So this is the big. So let's let P and Q be in the intersection of the attaching sphere of the K plus 1 handle and the belt sphere of a K handle. And I'm going to abbreviate these P, Q. So now, these are spheres. If we're careful, we can avoid spheres that are disconnected because our manifold has a boundary component, so you can actually construct a handle decomposition without 0 cells. The technical thing that's swept under the rug. But we can assume that laws of generality that P and Q are connected. And so we can choose a path, gamma P, going from P to Q to P, and a gamma Q going, say, back from Q to P to Q. So this means that if we do gamma P and then gamma Q, this is a loop in boundary component of W. Boundary component N. So if I1M is 0, this means that, so if we consider this loop as a map from the circle into N, this extends over disk. So we get a map from D2 into N. That's a good start. So here we've used simple connectivity. This is like, aside from translating everything into homology, which was a really, really, really big part of the proof at a conceptual level, this is the other crucial part where simple connectivity comes into play. It's in order to find an actual disk spanning these things. So the picture is good. So we start with the picture of Q intersecting P. Say this is P. Q is going through like this. Say here's a plus and here's a minus. I forgot the crucial assumption. These have opposite signs. So the orientations of P and Q will give you a plus at P and a minus at Q, or vice versa. And so we have this to start. And then what we've just done is we've chosen these two paths, gamma P and gamma Q.
say that this is gamma P, so this is gamma Q. And gamma P maybe goes around this way. Okay, and then we've chosen an extension of the disk. I'm not going to draw yet because it's not what we want entirely. If, moreover, so the boundary dimension, all of this is happening in the boundary. Moreover, dimension of the boundary is at least 5. You can choose a disk to be smoothly embedded. Like I said, this is due to it. This is the Whitney embedding here. People understand how differentials, how it's also why this is called the Whitney. So we can choose this would be smoothly embedded. So let's say D smoothly embeds D2 into F. So here's our D. Q, B. So this gets the name written disk. Ever remember C or K? So this is actually really close to being done. Doesn't really seem like it. But once we have this disk, there's a very clever and tricky and technical argument, Whitney trick, where we can use this disk as a guide to take P and pull it back so that it misses the disk and misses P entirely. And the trick is pull P back.
P surface or the curve?
P is the surface.
Okay.
Yeah, we're going to leave the Q part alone.
Yep.
And then we're going to do it. It doesn't really, it's like completely symmetric. Actually, what we would, you could take the curve and pull it back. The picture in the bowl looks way cooler, so we'll do that. Pull it back along P until this is Q. So what does the picture look like?
Yeah.
Part of it. Comes around like this. So this is like all of the surface, and then Q is just passing through
Yeah.
untouched. So we have separated our two things, and canceled out these two intersections. So here we use I1 and 0. Here we use our dimension of the function. Both of them in the middle. Like I said, we use this a lot more just to translate everything into homology. But I forget this might be possibly the only place that we actually have anything.
Because now I'm just imagining the picture. If you take gamma Q to pass through P, but it's on the boundary, like, do you mind if I come up and?
No. Yeah, you have to remember that the Q has to pass through Q itself.
Yeah. Yeah. But like, what if it hits? What if it's here? So like, if I draw this picture again, like.
Because this is just like a schematic.
Yeah, but if my gamma Q, okay. Oh, okay. Yeah, okay. Because then my question was here, like if it was like this, then you wouldn't be able to separate. But yeah.
I would just say like, draw more.
Yeah,
Yeah, it was a good question. I forgot to actually mention that. This is, I've only drawn part of P and I've only drawn part of Q.
Yeah.
Both of them are closed manifolds. So you have to imagine that they extend into the rest of the blackboard or out of the blackboard. So that's the Whitney trick. So that lets us separate algebraically canceling points. We're not going to talk about Morse theory today.
5 minutes left.
It's okay. Not my favorite thing. Maybe a topic for somebody else for another time. I'm mostly. So this is the idea. So I've given all of this toolkit about handles, and so now that we've done all of the work, I guess I'll just verbally recap how the proof works because it'll take too long to write out. So the big missing part that we didn't actually do is ensure that a manifold has a handle decomposition. So what you do is you take your manifold W, your h-Cobordism W, and you choose a Morse function. And this Morse function gives us a handle decomposition that starts with M cross I, a little colored neighborhood, adds a bunch of handles until the opposite boundary is N. Okay? So that's fine, we have a handle decomposition. The assumption that M and W are simply connected and that this is a homotopy equivalence amounts to the fact that our H, our homology, the homology of the Kervaire. Actually, we didn't need simple connectivity. Simple connectivity makes that infinite. But this is a consequence of having an h-Cobordism. Yeah, this is a consequence of it being an h-Cobordism. So using this and our handle decomposition, which computes the homology, we know that our handle chain complex is exact. Exactness of this chain complex lets us do algebraic manipulations to make our boundary operators look really nice, like we had. Right? There's like 4 rank of 1s and then a bunch of 0s, and then, or you could have it something like that. So algebraically, we can change bases to do this, which corresponds to some geometric moves that I didn't talk about at all, that actually geometrically alter your handle decomposition in order to achieve these boundary maps. So in the boundary maps, the definition of the boundary map, the fact that they have these very trivial forms is just saying that for every k handle, it either has incidence number 1 with a unique k minus 1 handle and no other handles, or it has incidence number 1 with some k plus 1 handle coming down. So every handle just gets paired off perfectly to some other handle. So then, we'd like to take this incidence number unique to 1 and translate that into saying that they actually geometrically intersect endpoints. Now we can use the handle canceling theorem, like we talked about at the start. Once we've canceled all the handles, then it just looks like n cross I. So in order to achieve this, now some of our assumptions come back. We need to have, to make the proof work, use simple connectivity in order to construct a disk. The Whitley embedding theorem to make sure that it's smoothly embedded in it. And once we have that, some very technical arguments that I completely still over up, we can separate the 2 manifolds in kind of a region around those 2 maximum points to eliminate that intersection until we actually go from incidence number 1 down to geometric intersection. Cancel those handles. Once we cancel all the handles, we're done. Our h-Cobordism is equivalent. Exactly 2 hours.
I really like this one.
Oh, good.
This might be my top 3.
Sweet. Yeah, no, it's a really huge theorem and huge argument. I feel like things where like you can sit there and explain by concept how everything works, and then people are like, oh, okay, yeah, sure, it works. And then to prove it, it's like many technical difficult.
I was gonna say like how much are you like you just said that you're sweeping a lot under the rug there, but I'm curious how much else you actually swept under there.
Quite a bit. Like, it feels like unquantifiable. Like there's just so much that I flipped over and didn't really do carefully.
I love you.
Carefully, like I think it would be like an actual full-length seminar course for people once a week or something like that.
Wow.
Yeah. So yeah, like a lot of like graduate seminars in algebraic topology, like they like to use this topic as like their guiding topic throughout the seminar because you do go through a lot of the really core fundamental stuff that applies to a lot of other things, not just the h-Cobordism theory. But you still need to develop those things for you.
Yeah,
A lot of work.
Morse theory like outside of it, but I can't remember the context. What was it used for outside of this stuff?
Outside of this, I've seen it being used in the context of loop spaces to compute dot periodicity. I think that there's got to be lots of geometric applications that I don't know about.
One use of it is to identify if the space you're working with is a sphere by finding the homeomorphic, just up to homeomorphism, obviously.
Yeah.
Um,
So Daniel brought up a good example that I was about to mention. So the idea, like with the sphere, like if you just have the height function, like this is a Morse function with exactly two critical points. There's a theorem called Reeves' theorem that says if you have any closed manifold in a Morse function with exactly two critical points, then it's homeomorphic to the sphere. So this is how Milnor, in his original paper, he determined that thing he cooked up with was homeomorphic to the sphere. He actually wrote down the Morse function.
Oh wow.
Yeah, with one critical, two critical points. Yeah. Yeah.
I guess probably one of the most useful one for physicists as well.
Is it?
At least I haven't seen it being used outside of that for many cases, but yeah,
Yeah.
I've definitely seen at least one use of that for identifying spheres.
That's cool.
Yeah.
Yeah.
You could do it for Torah and whatever else as well.
That's pretty funny. I didn't know that you could construct the torus like that.
Oh yeah.
I was not expecting that. Like when you started drawing the handle, and then you added on that two handle. Like, what the
Yeah, actually, I had some drawings that I did that I kind of neglected to do. It's like at each step, like I manipulated to make it look more clear. Like, oh, come on, that is crazy. And once you add that handle there, you can see like how each side can be bent up to make like
Yeah.
an upward facing torus. And then you add the other one that like brings you back.
Yeah.
Well,
Yeah. That's so cool.
If you wanted to give like some closing remarks to kind of like whet our appetite for what can come next, or maybe open problems in this, or to kind of give like a sneak preview, food for thought, whet our appetites, you get the idea.
Well, corollary.
Oh.
The h-Cobordism theorem. If M is simply connected, and M bounds a contractible manifold, then M is diffeomorphic to the standard sphere. So this is the h-Cobordism theorem. So n is greater than or equal to 5. See? Yeah. So this is like the Kervaire and Milnor, like right out the gate. As soon as Smale announced his result, essentially, Milnor was like, I bet this is true. And it's actually a really easy proof. You basically just take your contractible manifold, you remove a standard ball out of it, leaving behind a standard sphere, and then you do a computation to show that that's an h-Cobordism between the standard sphere and your boundary M. By the h-Cobordism. So this is the start. This is how you can tell when something is different.
And this is what they use for their classification.
Yeah, this is how like they got off the ground.
Is it are they completely classified past 5? Or
For 5 and up, I'm pretty sure, yeah, there's like a complete final answer for a cyclic group of order something to do with the Bernoulli number, and then there's like some co-kernel of the J homomorphism, stable homomorphism, which is known by Adams's computations with the spectroscopy. It's wild.
Nice. Thanks for the talk.